All right, so hello everyone. This is going to be your PowerPoint for online module 2. We will be investigating different aspects of water quality. I'm going to share the screen with you and it'll be our PowerPoint. You can find this PowerPoint in the online module 2 folder. It is labeled ACISC102 water quality. Okay, so at this point you should be able to see the screen. And we'll start our PowerPoint. So our basic lecture outline for today will be, first we'll review some chemistry. We're going to talk about what nutrients are and how does that compare to toxins. We'll talk briefly about the nitrogen cycle. So the first part of this course, ACISC101, you might have talked about the different spheres, and within that, the different cycles, right? Perhaps you learned about the carbon cycle, the water cycle. Well, we're going to be reviewing some of the nitrogen cycle. We're going to talk about the impacts of excess nitrates and the sources of nutrients, as well as how do you deal with them. So some management. So first things first, you guys need to know what a solution is. So from basic chemistry, perhaps maybe you learned about it in high school chem. If you haven't had chemistry, that's okay too. I'm going to tell you exactly what a solution is. And basically, a solution is a solute plus a solvent. In this case, in this example, water here is our solvent, but water is not always the solvent. A solute is basically anything that goes into your solvent. So it's this like blue powdery stuff in this example, but it could be other things as well. So a solute plus a solvent is equal to a solution. Your solute, therefore, is your dissolved substance in a solution, and then your solvent is the dissolving medium in a solution. Water is a universal solvent. It's really, really important. This is why when we're trying to look for life in outer space, we're looking for water. And that is partially because it can do a lot of cool things. So it dissolves polar molecules, and we'll talk about what does it mean to be a polar molecule? Why should you even care about polar molecules? It also dissolves gases. So an important gas that it dissolves, particularly for ecosystems, is oxygen, right? Like fish in ponds cannot survive if they don't have enough dissolved oxygen in those ponds. So you probably have already noticed, right, that water can dissolve liquids like salts. If you put table salt into water and you mix it around, eventually you will not see that table salt anymore, right? And it kind of becomes one with the water, and it creates a solution. Now you still know it's in there, right? Because if you were to taste that, you'd be like, wow, this is salty. Liquids such as ethanol, so it can dissolve things like ethanol. Gases, like I just said, oxygen, carbon dioxide, they can all be in water. However, water cannot dissolve non-polar molecules, and we'll talk about, again, what non-polar actually means. Specifically, it can't dissolve things like hydrocarbons. So these would be things like motor oils or gasoline. And you'll notice in this picture over here, right, this is a picture of water not dissolving oil, which would be a hydrocarbon. It doesn't dissolve glass. So the water in this glass is not being dissolved, right? It's literally, the glass is holding the water. And plastics, right? If you put plastic in water, it's not going to dissolve anytime soon, and it will never dissolve, which is why we have a bunch of plastic floating around in our oceans, right? It's not getting dissolved or broken down, at least not by water. Okay, so what do we mean by non-polar and polar? So I mentioned in the previous slide, right, water can dissolve other polar molecules. It can't dissolve non-polar molecules. So what does this even mean? So that's where we're going to have to review a little bit of basic chemistry. So first things first, atoms are your smallest component of an element, and it retains all those chemical properties of that element. So the easiest one that I think might be easiest to understand is like if you imagine gold, right? You can imagine gold in your mind. That is an element in addition to being like a precious metal. But basically, that particular precious metal is also the smallest component that's retaining all of its chemical properties. So like the shininess of gold, how it reacts to heat or liquid or cold, right? all of that, all of those characteristics are retained, and that's how we know that like that is an atom, or the smallest component of that. And atoms are made up of protons, which are these positively charged components, electrons, which are negatively charged components, and neutrons, which kind of hang out in the middle in this nucleus with your protons. And the neutrons are neutral. That means they don't have a charge. Now, this is really important because atoms by themselves, they like to fill these outer shells. So this is known as your valence shell here, or your and these are your valence electrons. So these are the electrons that hang out on the outer shell. Now, for this particular example, this valence shell is super, super happy. Like it's got 2 of them, and that's exactly how many electrons it wants in that outer shell. However, other atoms don't have the same number of electrons, right? And so they're going to actually fill up a second shell, and depending on how many electrons get filled in that shell, kind of depend on whether it's willing to give away electrons, or if it's more inclined to take electrons from other atoms. And when it does that, we're talking about forming different bonds or having other interactions with atoms. So of course, atoms are really, really tiny. We can't see them, but they are certainly interacting with other atoms constantly. So this is an example of an interaction between atoms where electrons are shared. So instead of taking or donating an electron to another atom, they're actually sharing it equally. So you can see this carbon is sharing an electron with this hydrogen equally, because carbon basically wants to fill that outer shell I just talked about, but it doesn't necessarily want to steal or transfer electrons to hydrogen or vice versa. So instead, they end up sharing it nice and equally. Everybody's happy. Ionic bonds are formed when you have some positively charged ions. And basically what happens is, because sodium only has 1 little electron in its outer shell, it's actually going to be kind of looking to get rid of it. Because the fact that you have 1 out here makes it really unstable, and it really kind of does not like having that electron in that outer shell. So it's going to be more likely to try and get rid of it. Chlorine has the opposite problem. It really wants to fill this outer shell to become stable. And so it's actually going to be more likely to take an electron from another atom that kind of is in the opposite situation, right? It's going to take one from the atom that really wants to donate. And so when that occurs, they actually form what is known as an ionic bond, and this becomes an ion. So ions are basically charged atoms. So now you have a sodium ion and a chloride ion. If you need some more clarification on ionic versus covalent bonds, please watch this video in the lower right-hand corner. This will be really important and will help you understand these interactions. So now we're going to take this a step further. So we talked about 2 types of bonds that are formed, covalent and ionic, but you can actually divide covalent into another subset of bonds. So this is, oh, sorry, this is just like a zoom in of your ionic bond. So again, this is when a chlorine atom is going to actually take the electron from the sodium atom, and the sodium is going to want to donate it. When that happens, the sodium becomes positively charged. That is known as a cation, and the chlorine will become negatively charged, and that is known as an anion. All right, so now we're going to actually divide our covalent bonds into something more. So I did say earlier that covalent bonds are when electrons are shared between atoms, right? But you can actually divide covalent bonds into 2 different types. You can have a polar bond and nonpolar. So there are those words again. And polar bonds occur when you've got kind of this bully like oxygen here, which is extremely electronegative. That means that they're going to want to take electrons from another atom. So instead of just like sharing nicely, these guys are going to be kind of a bully, and they're not going to share so well, and they're actually going to kind of draw in hydrogen's electron that's like hanging out here towards the oxygen molecule, because they're kind of a bully. All right. And so when that happens, when you pull the electrons closer, right, to the oxygen, it's actually become partially negatively charged. So this particular diagram is a little bit wrong because this should not be a plus, it should be a minus. And then because hydrogen's electron is getting pulled towards oxygen, this is actually going to leave hydrogen itself with a partially positive charge. You can think of it as like if you're distancing yourself from some negative energy, right? You're more likely to feel positive about something versus oxygen, which is really pulling in that negative or that electron from each of these hydrogens. So it's become more negative. Does that make sense? If it doesn't, watch this video in the lower right-hand corner. A non-polar covalent bond is the exact opposite of that. So you can see here there are no charges on any of these molecules or any of these atoms, which means they're being shared completely equally. All right, so no charges are occurring. And then this is also another example of a non-polar covalent bond. It's actually just a double bond as opposed to a single bond. But all you need to know really for non-polar covalent bonds is that they do not have charges because those electrons are being shared equally. So this is an unequal distribution of electrons. Remember that oxygen is pulling in those electrons from that hydrogen. This is an equal distribution of electrons, which means there are no charges on any of these atoms. Okay, so why did I just like spend several minutes telling you all of that and possibly like having you guys watch more videos? Because what does polar versus nonpolar mean for solvents? So I told you that water can dissolve polar bonds, but it cannot dissolve nonpolar bonds. Well, water is a polar molecule. So remember, this means it has that partial charge on its hydrogens and oxygens. And because of this, water likes to hang out with other partially charged polar molecules. So an example might be NH4+, which is ammonia. So because it likes to hang out with these partially charged molecules, it actually can help dissolve them into the water. Because essentially, it kind of combines, right? You can think about your charges like attracting one another, right? Opposites attract. So plus is going to be attracted to a negative charge and then vice versa, right? And so when that happens, dissolution or the process of dissolving occurs. So this is why it's important to know if something's nonpolar or polar. Nonpolar molecules, remember, they don't have that partial charge. So they don't like to hang out with polar molecules, which is why they stay separated. So you can think about oil and water, right? Oil itself is a nonpolar molecule. It looks much like a carbon with a bunch of hydrogens. That's all nonpolar. And it does not like to combine with water, which is why if you put a bunch of cooking oil, right, in water, it separates itself out eventually. You can mix it up, but it still separates in the end. So that's important fact number one about water being a universal solvent and what does and does not dissolve in water. The other way that we can look at solutions is by their concentration. So the concentration of a solution is the mass of the substance, or the solute, remember, dissolved in a certain volume of water. So the more of a substance that you put into water, the more concentrated that is, right? And you can change the concentration of a substance either by adding more of the solute or more of the solvent. So in this lab, you're actually going to see a bunch of different concentrations of nitrates. We're going to be really focusing on nitrogen. And you might see it written a couple different ways. So you might see it as written as parts per thousand, or PPT, which is the equivalent of saying grams per liter. You might see it written as parts per million, or ppm, which is the equivalent of it saying milligrams per liter. You might also see it as parts per billion, or ppb, and that's the same as saying micrograms per liter. All right, types of nitrogen in solution. So again, nitrogen does not come in one form. Nitrogen can be in many forms. So you might see nitrogen as ammonia, which is NH3. You might see it as ammonium, which is NH4+. You might see it as dissolved nitrogen, which is essentially nitrogen gas into nitrite, NO2 minus, and nitrate, NO3 minus. So all of these are things that you might see in this lab, but they're all different forms of nitrogen. So this is also how you might see nitrogen reported. So you're going to be looking at some actual data from the EPA in this lab, and they're going to report nitrates in different units in different ways. So you might see it as ppm, you might see it as mg per liter, right? Because remember, milligrams per liter is the same thing as saying ppm. For the EPA, you might see it as nitrate nitrogen, which again is the same thing as nitrates. And that's just how the EPA reports it. You will definitely see that. And they also report it particularly in milligrams per liter. So they don't even use parts per million sometimes. And then the USGS will use a different method. They report nitrate nitrite nitrogen, which includes nitrogen from both nitrates and nitrites. So you don't usually find nitrites in very large amounts. So it's oftentimes recorded with nitrates, and that's what they report. Either way, these are all just ways to measure nitrogen. And we'll talk about like why you should care about nitrogen. Okay, so I want you to think to yourself and tell me, what do you mean? What do we mean when we talk about nutrients? So take a moment to think about that. What do you think about when I say nutrients? Maybe you think nutrients are chemicals that plants and animals need to grow and survive, right? You might have thought about vitamins. You're right. I got to get all my nutrients in so I can survive. And you would be right. Like, these are important chemicals for life. Water is a universal solvent again. So that means all life on Earth utilizes water to obtain and circulate nutrients. So this again is why we are really interested in how water impacts a lot of these things. Men are about 64% water by weight. Women are about 53%. When we search for aliens, right, we're always focused on finding planets that have liquid water because we know water is important, right? It can circulate and obtain nutrients. For plants, we might focus on primary macronutrients. So these would be things like carbon, nitrogen, phosphorus, and potassium. These are nutrients that plants absolutely need to survive. Secondary macronutrients would be calcium and magnesium and sulfur. Micronutrients might be copper, iron, manganese, zinc, nickel, molybdenum, and boron, silicon, cobalt. All of these occur in a much smaller amount, but they are still important for aspects of plant growth. And so micronutrients are basically, you need a small amount of these for biological function. So that means you don't need a lot of it for it to have a beneficial effect. So for plants, this would be something like copper. So they do need a little bit of copper, and that is helpful for their growth and reproduction. Humans, we need actually a little bit of cadmium and selenium. If we didn't have cadmium or selenium, we would not function properly. However, when you get too much of these nutrients, you can actually experience what is known as a toxin, right? So if you eat too much selenium, 100% it will be toxic to you. So these would be, when we're talking about a toxin, we're talking about a chemical, physical, or biological agent that causes disease or some alteration of the normal structure and function of an organism. So toxins and nutrients can be interchangeable. And the fact that if you get too much of a nutrient, it can become a toxin. An acute toxicity would be an immediate impact versus chronic would be something over a long period of time. You can think about your chronic toxicity like your LD50 curve, right? So even those plants that had lower concentrations of salts, for example, you might have noticed that some of those plants didn't grow as well, right? They might have grown, which was great, but they probably didn't look as good. So scientists are usually focused on when a nutrient becomes a toxin. So there are a few elements that pretty much you should not eat ever, which would be like mercury, arsenic, lead, thallium. All of these are pretty much toxic at a lot of concentrations. But for the most part, there is sort of this curve on when a concentration, this curve for when something becomes toxic. So concentration is going to dictate toxicity, meaning certain concentrations will be toxic, others will not. So again, think back to our salt toxicology lab. I stole this from one of the lab reports because it looked really lovely, and it does a great job of showing when some of these salts actually become super toxic. So if you look at CMA here, it doesn't actually take much, because right after 0.08 molar as our concentration, you can see here at 0.1, 100% of the plants died. Versus if you look at table salt here, this kind of yellowish line, it actually doesn't do too bad. And you might even say that some of this is within a normal range of how many seeds might actually sprout. But you can see when it gets to 0.16 and above, then it starts becoming more and more toxic. So the real question is nitrogen a nutrient or a toxin? Nitrogen is really important for organisms and plants specifically. If we didn't have nitrogen, they certainly wouldn't grow as well. It's often considered somewhat limiting in some ecosystems. In fact, 80% of our atmosphere is nitrogen gas. So it is kind of everywhere. Plants can only take up nitrogen in two forms, from the soil and water. So it makes nitrogen kind of this limiting nutrient in plant growth. So, I mean, in that case, yeah, nitrogen is acting like a nutrient. But an example would be ammonium. If you get too much of that in the soil, this can be extremely toxic to plants at high concentrations, and it's a big component in animal waste. So if you are in an area where there's too much animal waste, like, things won't grow anyway, right? Because there's too much ammonium in the soil. Nitrates, they can be toxic to humans. If you drink water that has above 10 milligrams per liter, or 10 ppm level of nitrates in it. Blue baby syndrome occurs in children when nitrogen actually binds to hemoglobin, and it causes asphyxiation, which basically means they can't breathe. So in some cases, while nitrogen is super important for plant growth, it can also be really toxic. All right, the nitrogen cycle. So this is the nitrogen cycle basically in words. This is looking at the different processes that connect different parts of the nitrogen cycle. You do not need to know necessarily, like, this is how you write out oxidation of ammonium, but you do need to know the terms fixation, mineralization, nitrification, and denitrification. So basically, you need to know what those kind of mean. So you don't have to give me a chemical formula, but you do have to know what they mean. So for example, for fixation, you need to know that this is where it converts nitrogen gas to something usable, to a nitrogen that is usable, which is nitrate. Mineralization, you need to know that this is when you have decomposition of organic matter, and this produces ammonium. You will have to know what nitrification means. So this is the oxidation of ammonium to nitrite, or, and it includes the oxidation of nitrite to nitrate. So basically going from ammonium to nitrite to nitrate. And then denitrification, you need to know that this is the conversion of gas, or conversion of nitrate to a gas, right? So completing that cycle again, right? Because this was the conversion of a gas to nitrate. Okay, so this is kind of what our nitrogen cycle looks like in general. You've got your plants here, you've got nitrogen fixing bacteria that live in the roots. You've got your decomposers, so you can think about mushrooms. You've got animals that are contributing to this, right? Because they have waste products. And you've got your nitrates, your nitrites, ammonium, right? Because that is from your decomposers and your waste material, right? So you need to know how you get to each of these parts. So these arrows are important to know. Like, what is lightning doing here? It's actually going through nitrification. And we're going to We're going to go through this on the next slide. So at this point, I would pull out kind of a blank sheet of paper so we can go over drawing the nitrogen cycle. So you're going to be, one, identifying reservoirs. You should have at least 4 of those, and that is basically where nitrogen hangs out. And then you should identify your flux mechanism. So that's the process that moves it from one to another. Your flux mechanisms are going to be these, right? Fixation, mineralization, nitrification, denitrification. So this is something that I drew for you guys. So you've got your animals, they're going to eat plants and produce waste. All right, that waste is going to go to your decomposers. That waste is in the form of ammonia, right? So they're going to mineralize that, which your decomposers are going to convert decaying matter to ammonia. Then it's going to go through nitrification, right? Which is essentially turning nitrates into a gas, right? Bacteria is going to help you do all of this. We have different types of bacteria. You have some bacteria that fix nitrogen. You have some bacteria that do the opposite, as in they turn it into a gas. You have some that also help plants decompose and mineralize things. All right, so there's different types of bacteria. Nitrogen fixation can happen 2 ways from the atmosphere. Bacteria and plant roots can help this, and lightning can actually fix nitrogen in the soil, and it creates nitrates, right? And nitrates, remember, in that soil are things that plants can use to actually grow. And again, you've got nitrogen fixation by bacteria in the plant roots, and then animals, of course, can eat the plants, and they also produce waste, right? So it is a bit complicated, but you can connect these things in many, many ways. Okay, so what happens when you have too many nitrates? So I just talked a whole bunch about how nitrates are really, 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 really important for growth. And so when you have too many nitrates, you have kind of the same problem. At least when it comes to plants, you have an excess of plant growth. And so, for example, in rivers and lakes, you might see this really big growth of cyanobacteria blooms. In drinking water resources, if you have some in the water, right, you might be exposed to a lot of toxins, and this, of course, can be detrimental to health. In estuaries, you can have areas that are hypoxic, meaning they don't have any oxygen, and that's because there's so much plant growth and decaying matter that it's actually taken all the oxygen out of the water. So what is cyanobacteria? I just said that a lot of excess nitrogen can contribute to cyanobacteria blooms. And these are these little single-celled plants. They float within the water column. They're pretty normal. They're really important for developing oxygen. So normally they do some really great stuff for us. However, when they get a little bit too much nitrogen, sometimes they go a little bit crazy and they overgrow. So this is the atomic ratio of nutrients of carbon, nitrogen, and phosphorus found in ocean phytoplankton. So it should be about 106 molecules of carbon to 16 of nitrogen to 1 of phosphorus. So this is like an ideal ratio for normal growth. If you have more than that, though, then it's assuming that the limiting nutrient in that lake is nitrogen, right? So if you've got 2 moles of phosphorus for every 16 moles of nitrogen, so like if you had 2 here instead of 1, then nitrogen in this system would be limiting. And so therefore, if you add nitrogen, it's going to cause a lot of growth. And that's usually what happens in these scenarios. So most lakes are phosphate limited. So usually you've got plenty of carbon and nitrogen. You probably have a lot of nitrogen because you've got a lot of decaying organic matter, right? So when things die, it turns into ammonia, and ammonia is part of nitrogen. And if you just add 1 more little bit of phosphorus, then it's going to allow it to really amp up some growth and promoting a lot of phytoplankton production. And then you get something that looks like a cyanobacteria bloom. So when the conditions are right, it will grow and it will grow a lot. And these are called blooms. And while blooms kind of sounds nice, they're actually a little bit gross. They produce this thick green scum over the lake surface. They're not very nice to look at. They smell, and it's not really great for tourism. They look like that. It's kind of gross. It's not great. This is an example of a bloom in Lake Erie, so one of the Great Lakes, not very far away. And again, that water looks really gross, green. It's definitely smelly. So why should you care about these blooms other than the fact that you're like, ew, that's gross, right? You should care because these blooms can also produce things known as cyanotoxins, which can have really harmful effects on your health. So it can result in gastrointestinal problems. You can have hay fever symptoms. You can get skin rashes. If you ingest enough of this neurotoxin known as BMAA, it might actually cause things like ALS, Parkinson's, and Alzheimer's. So that's not great. And I just want you guys to know, like, cyanobacteria are pretty normal. They're always present, but they do not always produce this toxin. And we're not really sure what environmental triggers causes the production of this toxin. So I'm just letting you guys know, just because there's cyanobacteria does not mean this toxin is floating around. But these blooms certainly have a fair amount of these toxins. And then, of course, as you know, Chicago obtains its drinking water from rivers and lakes, specifically Lake Michigan, right? So if a bloom happens in Lake Michigan, that's going to threaten our drinking water supply. So this is why it's important to understand how these nutrients function in these ecosystems. So here is an example of the Lake Erie bloom that occurred in 2012. You can see all of the sediment and algae hanging out here. A ton of cyanobacteria here hanging out in Detroit and near Toledo. And Toledo has a population of almost 280,000 individuals, so that's a lot of people. So think about Chicago and Lake Michigan. This is an example in Lake Atitlan in Guatemala. And again, you can see that bloom here, and this really impacted tourism for this lake. So there are social impacts for these blooms, not just like medical impacts, right? It doesn't look great, they don't smell great, and you can lose a lot of money on tourism. All right, so that's one process. So those are like cyanobacteria blooms. The other one that we're going to talk about today is eutrophication. This is also a natural geological process, and this often occurs over thousands of years. And it's a very slow aging process by which a lake turns into a marsh, which then becomes terrestrial again, which is really, really cool. Eutrophication occurs when the lake becomes so rich in nutritive compounds. So we're talking about decaying matter, lots of plant matter, that nitrogen, phosphorus, and other plant life become so abundant, they choke the lake with its organic matter. So eutrophication is an important part of life, but human activities often speed up this process, which is not necessarily a good thing. So this is an example of like a natural process, right? So this is a kettle pond in New York. It's in the advanced stages of eutrophication. You can see that there's only a little bit of water left. There's a bunch of plants surrounding it. But other than that, everything looks kind of okay. And this is what it looks like now after filling in. So you can see that it's completely filled in. There's no more lake, and it's now grass, which is really cool. So eutrophication itself, though, can have really large impacts on ecosystems and fisheries in particular. So we mentioned earlier about how hypoxia can impact an ecosystem. Hypoxia basically means low oxygen. So hypoxic waters have a dissolved oxygen concentration of less than 2 to 3 milligrams per liter. So also in this lab today, you'll be looking at some various concentrations and deciding whether or not a fish can survive in that. Most fish need at least 4 milligrams to live, 4 milligrams per liter to live. So if you have more than that, you're good. If you have less than that, your fish is probably dead. Hypoxia generally occurs when you have dead plant matter or dead cyanobacteria that settle to the bottom of the water column. They start to decompose. That process of decomposition uses oxygen. So when you use up all your oxygen, then you end up with hypoxic waters. And that's going to force fish to either swim away, so they might abandon an area, or they might die, right, if they can't swim anywhere. So this is an example of a fish that has undergone some hypoxic conditions. They can't really breathe. So here's our general summary of the impacts of nutrients. Blooms, they're ugly and smelly. People don't like them. They affect tourism. They can also have an impact on your drinking water, right? Blue baby syndrome is where nitrogen binds to hemoglobin in the blood and causes asphyxiation or the ability to not breathe well, right? Cyanotoxins, right, can have a lot of health impacts. Accelerated eutrophication is not good, right, because it can actually kill a bunch of fish, right, because it can lead to things like hypoxia. And interestingly, so not in addition to killing wildlife in like lakes, for example, it can also form wetlands at much faster rates, which can be a good or a bad thing depending on what's happening. Okay, so how do we get excess nutrients into ecosystems? Well, you might have thought of perhaps the more obvious choice would be things like fertilizer, right? We do a lot of agriculture, we fertilize our crops, and whenever it rains, all of that fertilizer gets dumped into our lakes and our rivers, right? And fertilizer has very specific combinations of nutrients in it. Specifically, it has nitrogen and phosphorus because those are both things that help plants grow. So if you add more fertilizer, you probably have a higher crop yield, you get more money, right? So right there, there's no incentive to really conserve this. And we're going to talk about two different sources of excess nutrients. So we have non-point sources and point sources. Non-point sources are going to be our indirect effects. Point sources will be our direct effects. So in this case, runoff from agricultural fields due to fertilizer is going to be a non-point source. Now, the other one that you might not think about is wastewater. So this is something that might occur in cities. This is going to contain excess carbon, nitrogen, and phosphorus that are not used by animals, because this is all wastewater. We might have a direct input or a point source from wastewater treatment plants or septic systems. And again, runoff again. So if you have runoff either from like animal feedlots or mega farms or even your own yard, right, can contribute as well to sources of excess nutrients. And these are, again, these are going to be kind of non-fertilizer options. Okay, so this is just kind of a breakdown of nitrogen pollution in the Virginia area. So you can see that a lot of their nitrogen pollution is just from sewage industry and agriculture. So can you imagine if you just managed to kind of fix this part of the sector, right? If you managed to reduce some of the agriculture nitrogen pollution, that would do kind of amazing things for how much nitrogen pollution occurs in the Chesapeake Bay. So I want you guys to think about that in the Chicago area, especially since we're trying to kind of keep Lake Michigan nice and clean. So I want you guys to also think about to yourselves, like how you might manage the impacts of excess nutrients, right? So Illinois, aside from Chicago, right, maybe not in the Chicago area, but just outside of Chicago, a lot of farming happens. A lot of those rivers are going to be impacted by farming practices and activities, and they certainly fertilize their crops. So how would you manage the impact of that? So take a moment, think to yourself, maybe write it down. This question's coming back later. Can you think of any challenges? So when you're thinking of challenges, I want you to go back to those New York Times articles that I had you guys read before this lecture. And I want you to really think about, the challenges that those individuals faced, specifically when they were talking about the farms in Iowa. So this is what the federal government does to help manage some excessive nutrient pollution. We have what is known as the Clean Water Act. And really the Clean Water Act is actually a series of acts that are federal. That means every single state in the union has to follow these rules. And it includes the Water Quality Act of 1965, the Pollution Control Act of 1972, the Clean Water Act of 1977, and the Water Quality Act of 1987. And the goal of this act is to really restore and maintain the physical, chemical, biological integrity of the nation's waters. So without this act, that means that states could kind of do whatever they wanted. And you can imagine that states that are really into farming might have a different response than those that don't farm as much, right? So think about just like within our own state of Illinois, where if you were in the Chicago area, you might not care so much about farming, but if you were in the more rural parts of Illinois, farming would be a big deal to you. And that concludes our lecture on water quality. So make sure after you watch this, you should start your lab and homework assignment for water quality in online module 2. And with that, we will end this recording.